Electric mobility. The graph now on screen shows the market capitalization for the main auto manufacturers after shares in Tesla became publicly available. For the years before 2017, traditional auto manufacturers such as Toyota, Volkswagen and Mercedes-Benz were the market leaders, but then Tesla made its entry into the top 10 lists and the rest is history. Tesla's obvious success is not only because of environmental concerns about traditional auto technology or government subsidiaries, but also better design, lower maintenance requirements, robustness and the smart features inherent in electric mobility. In short, battery electric vehicles, and in particular Tesla, have totally disrupted the marketplace, as shown by the fact that Tesla have become by far the largest auto manufacturer in the world. But what about heavy-duty vehicles, such as electric trucks, aircraft and ships? There are many research programs active in this area, and a few commercial solutions have already reached the market, but the main challenge is that of limited range. In other words, energy storage is the problem that requires a solution. Some companies have taken the approach of putting large numbers of battery packs into their trucks, for example, the 400 kWh battery packs on the electric Actros truck, but even with large amounts of storage, the range is unable to exceed 400 kilometers. Other approaches to the problem have involved using fuel cells combined with hydrogen tanks, or even using hydrogen as a drop-in replacement fuel in specially adapted combustion engines, to increase range, but the improvements in range were negligible due to the fact that hydrogen energy density is a fraction of fossil fuels, and so this technology did not deliver a viable solution. Conventional thinking indicates that developments in battery technologies will eventually deliver significant increases in energy density in batteries. But energy density will need to increase tenfold to deliver commercially useful ranges for electric trucks, aircraft and ships. These sorts of improvements to energy density is simply not predicted to happen even by the most optimist proponents of current battery technologies. For electric aviation, the problems are even more acute than for trucks and ships. Even if there are big technological improvements in battery storage and hydrogen tanks, these solutions cannot work in the context of e-aviation because they're simply too heavy. For e-aviation, maximum takeoff weight is the limiting factor, so when a lot of battery packs or hydrogen tanks are installed in an electric aircraft, net payload dramatically decreases, which means that the e-aircraft can carry either fewer passengers or less cargo, thus reducing profitability substantially. To be commercially viable, electric aviation needs to solve one of the biggest challenges in aviation. Either solve the problem of energy density, which the graphs tell us is at least a generation away based upon current technologies, or find another solution. Our solution for e-aviation not only delivers better savings in CO2 emissions when compared to existing battery solutions, but can considerably improve safety, by carrying less fuel and batteries in the first place, delivering higher net payloads for better efficiency and with fewer technical stops. How do we achieve this? Through our unique approach, SKYCHARGE.
So basically, with this innovative solution, electric aviation is not just about emissions, but also effectively improve the efficiency and safety of the flights. Like when you are flying a 747, the fuel consumption is something like 12 tons per hour, which means that for an 8-hour flight, you need to take off and carry 100 tons of the fuel, right? Even for developing technology for the electric aircrafts, for a small aircraft like 9 passenger or 10 passenger, they are putting 1,000 or 1,200 kilowatt hour of the storage, which is too much to take off and carry. And some of them, to just extend the range of the aircraft, they are putting the hydrogen tanks and fuel cell to extend the range of the aircraft. But even with that, they are not exceeding 400, 500 kilometers. So they are working on that, and they are waiting for the big improvement in the battery technology to have much more energy density in the batteries.
Installation of the satellites into geo-orbits is the major expense, but costs are decreasing all the time and the advantages are manifold. They generate energy 24/7 at much higher efficiencies due to lack of reflection and absorption by the atmosphere and a better constant orientation towards the sun. Other options do also exist with more economic low Earth orbits, LEO, similar to those used by the Starlink satellites, but optimized to provide as much solar irradiation as possible. SKYCHARGE is based upon technologies that are available now, namely space-based solar power and wireless power transmission, also known as power beaming. Already we have seen solar power satellites launched into geosynchronous, GEO, orbits, where satellites travel to match the same speed that the Earth rotates at the surface. These space-based solar stations harvest solar energy using ultralight, high-efficiency modules, converting solar power to radio frequency, RF, transmission, and delivering clean energy to ground-based antenna potentially at the scale of gigawatts. These systems use microwave beams in the 8 to 10 GHz range, which are non-ionizing in nature and with intensities that are lower even than sunlight, so the systems are clean, safe, efficient and have been calculated to be price competitive with ground-based solar power.
In SKYCHARGE, what we designed is to achieve the range extension for the electric aircraft to use a network of the satellites in LEO to receive the clean energy from solar and convert it to an energy microwave beam, which is 100% safe, non-ionizing, and intensity less than sunlight, and lock it and send it to an aircraft down there and transfer energy to that. So they don't need to carry too much batteries, hydrogen tanks or fuel tanks, so that considerably increase the net payload and safety of the flights, and also there would be no technical stops, so they can fly limitless in the range, in the zone of the covered area, and zone of the covered area can be increased easily with the number of the satellites in LEO. So we calculated that for a transatlantic flights to cover the whole North Atlantic zone, we just need 16 satellites in LEO to cover the whole flight time.
Satellites in LEO can either generate power themselves or receive the power from geosolar stations, acting as solar relays and beaming the power onwards, utilizing the latest technology to lock phased array microwave beams to receptors nearer to the Earth's surface or, in our proposal, an electric aircraft along its flight path, or a ship moving between ports. In order to cover the whole North Atlantic area, we calculate a need for around 16 LEO satellites flying in specially designed orbits between 500 and 700 kilometers, using smart communication systems to select the most appropriate satellite to deliver a locked energy beam to an aircraft or ship's antenna and charge the onboard battery arrays. This obviates the need to carry tons of storage or fuel, provides, theoretically, limitless range and removes the need for technical stops, resulting in significant improvements in net payload and safety. All this has the potential to revolutionize the whole aviation and shipping industries, not just by drastically reducing emissions, but through vast improvements in efficiency and safety. This is possible due to our innovative solution we have termed SKYCHARGE. When an aircraft departs from Heathrow Airport, London to JFK, New York, the closest LEO satellites will deliver phased array energy beams to provide power during the whole flight, thus removing the need to carry whole flight battery or fuel loads. The same applies to a ship from Shanghai port to Dubai, with the network of LEO satellites detecting energy demand requests from the vessel and delivering the power beam to charge it in the SKYCHARGE zone of coverage. Our proposed SKYCHARGE system currently includes super-efficient space-based solar stations in GEO orbits to generate the power, partnering with a network of LEO satellites to manage charging procedures to include communication between other satellites, the eBirds or ships making charging requests, and relaying the required energy using lock and send energy beams to receivers in the SKYCHARGE zone. The number of LEO satellites required will depend upon area of coverage required. We calculate this to potentially be a very efficient way to keep eBirds or ships charged during their missions, and can be price competitive because it's based principally upon the use of LEO orbits, which can be developed gradually starting from a defined zone to cover a popular route, for example LHR to JFK, then scale up the LEO satellites network to eventually achieve whole Earth coverage. We therefore propose that investment into development of this technology is a priority and could lead to disruption of the whole aviation and shipping industries, solving all the major technical, commercial and environmental challenges at the same time.